Previously, we talked about how to use the EM algorithm to estimate the model parameter theta given a sequence of observation x1 through xn. And naturally, once we estimate the parameter theta, we also want to know what can we see about the latent states z1 through zn. And for example, what would be our best guess of those latent states? And there are two different solutions depending on the definition of optimality. One solution is choose the hidden states zt such that they are individually most likely, meaning at every time t, we're going to based on our estimate of theta, and we can compute this conditional probability of zt equal to I given x, and which is basically our gamma ti function we discussed before. So given theta, we can compute the posterior distribution of zt given x, and then we can just choose our best guess for zt to be the most likely value at zt. And this solution is optimal in the sense that if we want to minimize the discrepancy between our guess and the actual latent states, and this solution is actually minimizing that discrepancy on average, meaning it maximizes the expected number of correctly identified states. However, the resulting sequence may not even be a valid sequence. For example, we could have our individually best guess at time t to be 1, at time t plus 1 to be 2, but our transition matrix actually implies that it's impossible to transit from 1 to 2. So this leads to another solution for the latent states, is to find the most likely single sequence. Because given the parameter theta conditioned on the data x1 through xn, we could find the joint distribution of z1 through zn. How many different values of the sequence, how many different sequences we're talking about? Well, suppose my mz is equal to 3, so we have 3 latent states. Then all possible sequence of length n, and every position can take a value 1, 2, 3. All possible sequences would be 3 to the power n. So this is trying to pick the among the 3 to the power n sequences, which one has the highest probability, and that will be our most likely single sequence. Apparently, the computation is going to be difficult because, as I mentioned before, it will be difficult to keep track of a distribution with 3 to the power n different values. So the solution for hidden Markov model is obtained through a dynamic programming method known as the Viterbi algorithm. And first, we're going to define something called the delta t sub I. So you can think about your delta as a matrix where t is the first dimension. So we have n rows, and I would be the number of hidden states, which would be 3, for example, if you assume mz is equal to 3. So the delta would be a n by 3 matrix. Next, I'll show you how we're going to fill in this delta matrix row by row, okay? So what is the definition of the delta? What is the value of the tth row, which is delta t and I? It is the highest probability of a latent sequence z1 through zt, and also the observed sequence x1 to t, but we require the latent states should end at I, meaning z sub t is equal to I. So that's the definition of delta ti. Let's first fill in the first row of delta. For first row, there's no maximization involved. It's basically the joint probability of the z1 equal to I, and also the observed sequence is x1. So next, we're going to sequentially fill in the rows of the delta matrix. Suppose we have filled in the rows from row 1 to row t, and next let's fill in row t plus 1. So delta t plus 1i by definition is equal to the maximum joint probability of z and x from time 1 to t plus 1, and also we require the latent state at t plus 1 and is equal to I. So we can factorize this joint by some kind of marginal and the zt plus 1 conditioning on all the previous variables. It turns out it only depends on zt, and then xt plus 1 conditioning on all the other variables, and it only depends on zt plus 1. So this is basically the transition probability, and this is the emission probability. And for this term, if we take one of the max outside, max over j, and then you will see that this basically is delta tj, which we computed before. So we can rearrange it, and we can find out that the t plus 1th row of the delta matrix can be recursively computed based on matrix A, B, and also the previous row of the delta matrix. And there's some interesting fact is that the whole idea is very similar, computation is very similar to the forward probabilities alpha. And the only difference is that in the delta computation, we max over j, but in the alpha calculation, the forward probabilities, we average out all possible j's. After computing the delta matrix, which is a n by 3 matrix, where we assume mz, number of hidden states, is 3, then we're ready to solve for the most likely single sequence z. And z is defined to be the most likely value, the value of z that maximizes the conditional probability of z given x, but the conditional probability is equal to the joint of z and x and divided by the marginal of x. And the marginal of x has nothing to do with the value of the latent states. So it is okay to view this maximization as a maximization over the joint probability of z and x. So I change that bar to be comma of x. Now let's solve this z backward based on the delta matrix. Let's look at the last row of the delta matrix. There are 3 entries, and each of the 3 so there's 3 entries here, 1, 2, 3. For example, this store the highest joint probability of a z and x, where the last hidden state for z is 1, and this is the highest joint probability for z and x, where that z sequence ends with zn equal to 2, and this is the corresponding joint probability for zn equal to 3. So apparently, which one maximizes the probability would be the most likely value for this z star n. For example, suppose the second entry is the largest, then we know that for this most likely single sequence z, its last value must be equal to 2. Once we solve this, and zn star equal to 2, and then let's go back to look at what is the most what is the value for z star n minus 1. And we're going to look at the last second row of delta matrix. 3 values here. And each of the values represent the joint probability of z and x all the way from time 1 to time n minus 1, where the z n minus 1 ended with 1, 2, or 3. So apparently the probability which one is the largest that means it's very likely that that value could be the value for z star n minus 1. But we also have to consider that now we know zn is equal to 2 now based on our previous argument. So what we need to consider is not only the value of delta n minus 1, but also the transition probability from I to 2, because we know this is equal to 2. So what you're going to find out, what we need to maximize is a product of delta times A. and the value I, which is from 1 to 3, that maximize this product, will be the value for z star n minus 1. So we can do this sequentially, starting from z star n minus 1, all the way we can solve z star 1. So put them all together. That's the most likely sequence. And this algorithm is known as the Viterbi algorithm.